Okay, we'll be maybe start the session on type-driven types. So, one goal of the session, I guess, is to answer the question what it means type-driven types. And the first talk is we'll answer another question: is that what happen when you put linear types into the calculus of constructions, of inductive constructions?
Yeah.
That's kind of my take on this talk. So it will be given by Qiancheng Fu,
yes.
And it's authored by Hongwei.
Yeah.
So please go ahead.
Okay. Yeah. So hello everyone. My name is Qiancheng Fu, and thanks for coming to my talk on the calculus of inductive linear constructions. This is a joint work between me and my advisor, Professor Hongwei, and it builds on a lot of the lessons learned from the ATS programming language. If you have seen our paper, there's a lot of very gory technical details in there. So this talk aims to be the complete opposite of that and give a sort of high-level overview of the design choices that we made. So as the name of our work might suggest, we are heavily inspired by the calculus of constructions. And the calculus of constructions is a dependent type theory designed by Coq and Hewett. Types can abstract over terms, allowing for precise specification of its inhabitants. Here we have two of the most famous examples of that. We have the pi type, basically saying for all x of type A, there is something of type B. The sigma type says that there exists some x of type A, such that there is something of type B. Pauline and Coq extend the calculus of constructions with schemes for inductively defined types, forming the calculus of inductive constructions, which I will refer to as CIC. So, despite the great successes, no, I already got into too far into the talk. Okay, so the theory of CIC lies at the heart of popular proof assistants, such as Coq and Lean. Coq and Lean have seen great success in the formalization and verification of software systems and mathematics. Some of the most famous projects off the top of my head are ComCert, formalized C compiler written in Coq, the Rust Belt formalization of Rust inside of Coq. This is where all of the Iris framework actually originated from. And we have the four-color theorem proof in Coq, and this is where the MathComp library of mathematics inside of Coq originated from, is to prove the four-color theorem. And we have MathLib, which is a huge library of mechanized mathematics inside of Lean. However, despite the great success of applying Coq to software verification, we do believe that there is a bit of a disconnect between the CIC theorem and the software system it tries to verify. So CIC is inherently persistent, whereas programs verified are often stateful. So one can work around this by first encoding the syntax and semantics of the stateful programs they wish to verify into Coq, and then we can apply program logics such as Iris to reason about the state transformations. But on top of the really difficulty encoding work, which something like Iris is a very big engineering effort on itself, we also have to trust that the original program that we're verifying actually follows these idealized semantics, right? So what we wish to do is we wish to support stateful low-level programming directly in the dependently typed language without extra encoding work. So to accomplish this, we incorporate ideas from Girard's linear logic. And sort of the main tenets behind linear logic is that it restricts the structural rules of classical logic. So one of them says that objects cannot be discarded via the weakening rule, and then objects cannot be discarded via the contraction rule. So essentially, without these, when these two rules have been restricted, what happens is that you have a symmetry between introduction rules and elimination rules. But however, we'll see very shortly that merely restricting weakening and contraction is not enough to obtain a language with the memory guarantees that we design. So in many type systems inspired by linear logic, one finds these kinds of lollipop arrows with the following interpretation as a function type. So when we say a lolly b, this is the type of a function whose parameter of type A is used exactly once in the body of the function. So here's a very simple example of what we mean by this. So here we have a very simple lambda expression with a parameter x of type A and a body m of type B. And this says that the parameter x can only be used once inside of m. Okay, so what can we do with this? So it would seem that if we apply this linear lambda expression to some value v, that the v passed into x seems like it could be modified in place because it is used exactly once in m. But unfortunately, the parameter x being used exactly once inside of m itself does not actually exclude v from being referenced or used in the entire program. It just says it's being used locally once in m. It doesn't say anything about v being used in the entire program. So if we were to call a mutating function like free inside of m itself, then this could lead to the value v getting reclaimed prematurely, and you can run into different kinds of bugs. Additionally, function closures like the lambda expression themselves are resources at runtime. So how many times can we apply the linear lambda expression itself? So these are the questions that we would like to address. And in our type system, the modality, or linear or nonlinear, is an intrinsic property of the values themselves. And the variables that are in the language simply propagate the modality information originating from a value instead of actually determining it. And this ensures that the single pointer property holds for linear values globally, and it allows for safe in-place updates. So to determine the modality of a value, we use a two-sorted universe hierarchy system, similarly to Krishnaswamy's, to classify all types as either linear or nonlinear. So we have the sort U of all nonlinear types and a sort L containing all linear types. Though I want to point out, in our system, we do not need adjoint connectives or modal operators to go between linear and nonlinear things. And basically just using these two sorts and the universe hierarchy system, we are able to do that. So more formally, the modality of types and their inhabiting terms are determined by a couple of typing judgments. So for types, we have here, we say A is a nonlinear type because it inhabits precisely the U-sorted universe. And we say that B is a linear type because it inhabits the L-sorted universe. And for the terms that inhabits A and B, so for M, which inhabits A, we say A is a nonlinear term. And for N that inhabits B, we say N is a linear term. So here you can also see that there's some annotations on the colons, and these simply help to propagate the information of the sorts from the universe level all the way down into the term level. So we can see at a glance that M is a nonlinear term because we can see that the annotation on the colon is a U, and N is a linear term because the annotation on the colon is an L. Okay, so now we have the universes sorted out. We can start talking about the functions that inhabit them. So a pi type in CILC is of the following form: pi x colon a dot b. And then between these we have some annotations, sort annotations, S, R, and T, that ranges over the sorts U and L. So for the first two, sorts S and R, they inform us of the modality on the domain and the codomain. And the sort T, on the other hand, it's an annotation on the pi type itself. So functions inhabiting the pi U universe, pi U type, are allowed to be used freely, and functions inhabiting the pi-L type must be used exactly once. So these couple of annotations determine completely sort of the questions we have from before. So now we have the functional core of a linear dependent type systems whose values have intrinsically determined modality. So to encode data types in a general and canonical way, we include typing schemes inspired by CILC for defining inductive types. And both connectives from linear logic and intuitionistic dependent type theory can be uniformly encoded using these schemes. So here we define the tensor of linear logic and the linear sum. And also we have the intuitionistic sigma type. So by simply varying the sorts on the arities of the data type, we can define linear types and nonlinear types. The actual typing schemes presented in the paper is quite complicated, but as you can see with some type inference and stuff, the interface that we expose to the user of the language is actually pretty simple. And it's about as complicated as Coq. So now that we have a system for declaring inductive types, I want to turn our attention to their elimination principles. So in intuitionistic dependent type theories, one would use induction principles to perform primitive recursion over inductive types, right? So here we have the induction principle for natural numbers. Roughly speaking, this says for some proposition on natural numbers, if we have a proof H1 that the proposition holds on 0, and a proof H2 that says if the proposition holds on X, then it holds for Sx, then we can apply the induction principle and say that the proposition holds for all of the natural numbers, right? So I want to draw attention to this H2, the proof in the successor case or the inductive case. So notice here that the variable X here coming from the predecessor and the PX, which is encoding the sort of the recursive induction step. Suppose our natural number was a linear type, and this is something that you can actually define in our language, though I don't know why you would do that. But such a principle would be unsound because the X here, which refers to the predecessor, and this PX here, the X is simultaneously being kept as X and is also being used by the recursion or induction to compute the PX. So if the nats were linear, then this would obviously violate the no contraction principle. So instead of using induction principles for data, we opted to use a guarded fixed point and case analysis for primitive recursion. So here we have a user-written recursor for the natural numbers. So fixed point on the recursor, taking in a natural number, perform case analysis. When it's 0, return the proof H1. If it's successor X, we offer the writer of the recursor a choice between X or Rx. So for linear data, a user must decide to either keep X or to use it to compute the Rx part. And for nonlinear data, we can simply just apply contraction and obtain both X and the recursor applied to Rx. So this means that fixed plus case is equivalent to induction principles for nonlinear data. And for existing theorem provers that support guarded fixed points, such as Coq and Agda, we do know that the bugs in the implementation of the guard checker has led to consistency issues in the past. However, we believe that this combination of fixed plus case is cleaner than the alternative solution of providing specialized elimination principles for all usage scenarios. So in conclusion, CILC is a type theory combining linear types and dependent types. Our type system includes typing schemes inspired by CILC to enable the encoding of both linear and nonlinear dependent inductive types. We have proven the usual standard theorems, confluence, subject reduction, strong normalization. And using a heap semantics in style of Turner and Wadler, we show that CILC safely manipulates the memory of linear values. The majority of our meta-theorems have been formalized in Coq, and we have implemented a prototype compiler inside of OCaml. And there is still ongoing work. So currently, CILC only supports dependency on nonlinear terms. Recent work such as QTT show the possibility of such an extension. However, there is a bit of a trade-off to such dependencies in that non-monadic I/O effects are no longer possible. Also, linearity allows for the addition of session type-based concurrency. The inclusion of dependent types in general can greatly increase the expressiveness of session protocols within a unified framework. And we plan to extend CILC with more features and improve its expressiveness. And again, thanks to everyone here for attending to my talk. I'll be more than happy to accept questions and suggestions regarding our work. Thank you.
We have some time for quite a few questions.
Yeah.
Thank you. So you pointed out in the last slide that it only supports dependency on nonlinear terms.
Yes.
Maybe you talked about that. Maybe you had that in an earlier slide as well. But what does that mean exactly?
Oh, so like if we write a pi type, right? Like a for all something, that for all the variable, if it's dependent, then that type has to be a nonlinear type. Like let's say, for instance, let me go back to the slide here. Yeah. So for this thing, if we were to write this pi type, then this a here has to be nonlinear if we were to use x inside of b. If a were linear, then x cannot be used inside of b. So x cannot be a bound variable inside of b.
Thank you.
Another question?
Hi, that was a nice talk. I was just curious if you have anything equivalent to the bang and linear logic in your system?
No.
Okay.
No. Because we just completely use the U-sort for nonlinear things. And we actually think that this is more close to what happens in reality. Because if we have two universes that are completely distinct, what happens is if we have a term that is in the U, we can apply like reference counting and garbage collection to those terms. And if it's in L, then we don't do that. We can just use manual memory management so we can get very efficient representations for the values inside of the L universe.
Do you have some notion of polymorphism over universes? So that
That's a very good question. That's a very good question. Actually, in the most recent versions of this, yes, we do. But it's not at the theoretical level. It's kind of more like typing schemes where you can quantify over different sorts at top level functions. So when you apply them, it automatically infers the correct sorts, and then it applies the correctly instanced one. So basically, you do not have to write, but you can write a lot of these things that are generic over sorts. Yes.
So you're using sorts or primes to distinguish between linear and nonlinear, but
Yep.
something like QTT uses things like modalities. Is there, or like a type operator? Do you have any sense of what the trade-offs are between these?
Yes.
different
Yes.
mechanisms?
Yes. Actually, yes. So in the past, I've did some implementation experiments with QTT. So the issue is in the way that we handle we handle sort of the again, it's the pi types here. So in Qt, oh sorry, not the pi types, the lambda applications here. So in Qt, it marks x as 1, right? So you can use 1 only once inside of M. But if you pass a value into here, this value could be some nebulous thing that's defined elsewhere in the program. So even if you say, oh, this v is used twice, sorry, no, what's the Qt? The w many times, or a unlimited many times, and then you are allowed to apply v to here, but you can't do any optimizations inside of M to get rid of this x, right? Because if you do that, then your v becomes freed, and then you can't use, you're basically reclaim that v prematurely. So you can either do like a deep copy of of v whenever you apply it, so that this v, when you apply it, it's a new instance of v. But this is very costly in practice because deep copies are very costly.
I think the modal systems allow you to like create a box.
Yeah.
Allow you
But
to restrict v as long as, so not every v, I agree.
yeah.
You know,
But
you're
it's
talking
like,
about-
what do you take out of the box?
But if you make sure v stays in the box throughout the program, which is I
Yeah.
show you, that would give you more control.
Yeah. So what the box is essentially doing, it's storing data in there to recompute v every single time, right? So every time you fetch a v from the box, it's actually very expensive. So yeah, basically, yeah. But in reality, I think variables are actually the cheap things, because in implementation, we usually just pass around different pointers inside of the variables. So it doesn't really make sense to restrict how many times a variable can be used. The variables are linked to the values which we want to keep track of.
Okay, we can thank the speaker again and move to the next talk.